Alright, in the next chapter, we're gonna learn about milling, broaching, sawing, and filing. First, we will talk about milling. It's a machining process in which a rotating cutter removes material while traveling along a specified path. And then we will learn about planing, shaping, broaching, in which either the cutting tool or the workpiece travels along a straight path, producing flat or profiled machined surfaces. And finally, we will look at sawing and filing processes. In this figure, we are seeing typical parts and shapes that can be produced with the machining techniques that we're gonna learn in this chapter. As you can see, parts with complex external and internal features, gears, can be produced with these techniques. Milling is a highly versatile machining operation by which a surface is generated by progressive chip removal. The workpiece is fed into a rotating cutting tool, or the workpiece remains stationary and the cutter is fed to the work. In all cases, a multiple tooth cutter is used, so this provides a high material removal rate. And often the desired surface is obtained in a single pass of the cutter or the workpiece. The cutting tool used in milling is known as a milling cutter. And milling operations can be classified into broad categories like peripheral milling and milling face milling. And as you see, some of the examples of these milling techniques, milling operations and cutters are shown in this figure, and we're gonna see all of those. And remember to watch the videos also, because this way you can visually see the process. Here in this image you can see the cutting action of a milling cutter, and you are seeing that multiple tooth cutter that removes the material and generating the chip. In peripheral milling or plane milling, also called plane milling, the surface is generated by teeth located on the periphery of the cutter body, and you can see this in this image. And the surface is parallel to the axis of rotation of the cutter. The cutter body is usually made of high-speed steel and has number of teeth along its circumference, as you can see, and each tooth acts like a single point cutting tool. Both flat and formed surfaces can be produced by this method. And when the cutter is longer than the width of the cut, then the operation is called a slab milling. One of the aspects of milling concerns the direction of rotation of the cutter with respect to the movement of the workpiece. So the cutter rotation can be either clockwise or counterclockwise. So this is significant in milling operations. The up milling is the traditional way to mill and is also called, as you can see, conventional milling. In this one, the cutter rotates against the direction of feed of the workpiece. As you can see, the cutter rotates in this direction. The workpiece is moving in this direction. So that is, we can say the cutter is moving counterclockwise, right? In up milling. So in down milling, or we also call it climb milling, in that one you can see in the image the cutter rotation is in the same direction as the feed. So you are seeing the cutter rotating clockwise, and feed is, the workpiece is fed this direction. So there is a difference in between these two techniques. First of all, if you look at the up milling here, where the tooth comes in contact with the work, right? This part. So therefore, in up milling, the chip is very thin at the beginning because the chip is forming on the milled surface. So it is very thin at the beginning, where the tooth first contacts with the work. Then it increases in thickness and becoming a maximum where the tooth leaves the work here. And as you can see here, as the cutting operation begins it down, right, like this, and goes up, right? And we know the oxide scales are on top of the workpiece. Therefore, contaminants like contaminants on the surface, scales like oxide layers on the surface, they don't affect the tool life adversely, because first we are in coming contact with the workpiece in these regions, okay, where there is no oxide layer. But as you might notice in this case, the cutter tends to push the work along and lift it upward from the table. So therefore, as you might imagine, that this action actually tends to loosen the work from the fixture. So you need greater clamping forces because there can be chatter, and therefore proper clamping of this workpiece on the table is important in this operation. And in down milling or climb milling, you can see the cutting starts at the surface of the workpiece where the chip thickness is thickest. So maximum chip thickness occurs close to the point at which the tooth contacts with the work. Here the advantage is the direction of rotation of the cutter will push the workpiece downwards, so it is going to hold the workpiece in place. And because scale is hard and abrasive like oxide layers, right? And this can cause wear and damage to the cutter teeth, therefore shortening the life of the tool. Therefore, climb milling is not suitable for machining of workpieces which have like surface scale. For example, the metals that have been hot worked, forged, or cast. These are not suitable for this process. So let's look at face milling. And there's a mistake in the slides, so ignore this sentence. Okay, so the cutter, in this case mounted on a spindle, having an axis of rotation perpendicular to the workpiece surface. And you can see it in this actual image, right? So similar to previous technique here, when the direction of cutter rotation is as shown in B, like this, and the workpiece going this direction, then this operation is climb milling. And when the opposite is true, like shown in C, the workpiece goes in this direction, but the cutter moves along this direction, then it is opposite direction. That is called in this case conventional milling. So because of the relative motion between the cutter tooth and the workpiece, face milling leaves feed marks on the machined surface, like the ones shown here. Of course, these feed marks will depend on what type of insert you have, and this will change the effect. But you see in each case we have a feed marks on the machine surface when we do face milling. So as you can see, milling is done using inserts. Here you can see to remove the material from the workpiece. It is because these inserts are replaceable, right? They are made of carbide, and that makes them durable at extremely high temperatures and during high-speed applications. This way we increase tool life. And let's look at end milling. And we have seen end milling, right? If you guys remember. So this is a common operation. Again, in this case, the cutter rotates on an axis perpendicular to the workpiece surface. The cutter here is called end mill. End mills can be made of high-speed steels, carbide, or with coated or uncoated carbide inserts, similar to those we have seen in face milling. And in the first image here we are seeing a selection of end mills. The flute depth angles are selected based on whether it's a roughening or finishing cut. And here we also see some end mills are available with hemispherical ends. These are also called bold nose mills. You are seeing in this image. These bold nose mills, they are used for machining surfaces such as dyes, molds, and so can produce contours, and as I said, used in dyes and molds. So there are other milling operations and cutters. One of them is straddle milling. In this, two or more cutters are mounted on an arbor and used simultaneously machine two parallel surfaces on a workpiece. Like in this image you are seeing. So these are side milling cutters. They are often spaced on an arbor. So arbor is used for holding milling cutters, like this one right here. Another one is form milling. This produces curved profiles using cutters with a special shape, and such cutters are also used for cutting gear teeth. If you go back and here you see, so here is your arbor, and you can see it is the teeth is special shape. It has a contour like this, right? And there are slotting and slitting operations. These are, as you can see, performed with circular cutters, as we are seeing here, B, C, and D. And there are T slot cutters. They are, of course, as the name implies, they are used for milling a T slot. Here you see the T slot cutter, and to use this, the vertical groove must first be made with slotting to provide this clearance for the shank. And finally, there are shell mills. These are hollow inside and are mounted on a shank, thus allowing the same shank used for different sized cutters. Here you can see these are shell mills available in different sizes, and they are hollow, which gives us the flexibility that we can use them in a same shank and use different sized cutters. So while we are discussing, we discussed different tool holders. We say arbor. Some of them remember like slab face, straddle, and form milling. In this case, we have arbor. Arbor is driven by the spindle and provides the necessary length for the tool to reach the workpiece in these operations. In shank cutters, the cutter and the shank are one piece, and the most common example is end mills. So besides milling, there's planing. This is again a simple or machining operation by which flat surfaces, cross sections with grooves and notches can be made along the length of the workpiece, as you can see some of the images shown here. So this is typically performed on large workpieces, and if you watch the videos you will see in this case the workpiece travels back and forth along a straight path to shape the surface. There is a reciprocating motion, okay, back and forth, back and forth. Shaping, on the other hand, is actually similar. In this case, not the workpiece that travels, but the tool. And tool goes back and forth in reciprocating motion. And in this case, usually these are smaller workpieces. In broaching, we have a multiple tooth cutter. It is long. It is used to machine internal and external surfaces. Internal such as holes with circular, square, and irregular cross sections. Flat surfaces, teeth of internal gears, etc. And the cutting tool is called broach. In these figures, we are seeing typical parts made with internal broaching here, and parts made by surface broaching. And we see here actually a vertical broaching machine. Here is the broach here and the workpiece. So you see here a vertical broaching machine, right? So what happens? Broach is passed through the part, and then it is pulled through the part. Okay. So it can produce parts with good surface finish and dimensional accuracy. So the cutting, just the part is finished basically just in one pass, and this makes it a very efficient process. So sawing is a common technique, and we have a blade or saw that has a series of small teeth, and each remove a small amount of material with each stroke of the saw, and the chips that are produced are contained within the spaces between the successive teeth until the teeth pass from work. It can be used for all materials and capable of producing any shape. So the width of cut we call curve. is small, that process therefore wastes only little material. So concerning this, we can say this process is economical compared to other machining processes because it wastes little material. Here we see various sawing operations, and you see the saw is moving up and down, and we see ripping, we see it can form internal cuts, angular cuts, contour cutting, stack cutting, and wafer slicing. Here is your saw blade here, slicing the ingot. In the process of filing, the metal removing action is the same as in sawing, and in that chips are removed by cutting teeth that are arranged in succession along the same plane on the surface of a tool called file. The difference is the chips are very small here, and therefore the cutting action is slow but easily controlled, and the cutting teeth is much wider. Although filing is usually done by hand, there are machines with automated features that use burrs, attachments, and as you see in the images, these are used in die making or scale removal from the surfaces. They have different shapes. They can be flat, round, square. As you see in the images, there are different attachments, and if you watch the videos, you will see. So in this chapter we learned about milling, and we learned about different other techniques that are available to us. Like planing and broaching and sawing and filing, etc.